You just witnessed the production of standing waves. When you saw those standing waves produced at very unique and specific frequencies, you saw that those waves appeared to be standing still. You know that those standing waves, those waves that appeared to be standing still, were caused by interference, what we've been talking about for the past day and a half. Waves were traveling down one way, reflecting off of a boundary, coming back and interfering with the new waves that were traveling down in the original direction. In most times, that interference pattern appeared to be random, but at those very specific frequencies that we call the resonant frequencies, or the natural frequencies of the string, we saw an interference pattern that made the wave appear to be standing still. Now, the diagram that I have drawn here isn't the best. It's the best I could do with Microsoft Word. It's more circles than it is sinusoidal waves. You guys know that it's supposed to look like this, right? Sine waves. Okay, but, of course, the wave appears to be standing still like this. The tops of these waves, or in the bottoms, where you have the crests and the troughs, they're what we call antinodes. Those antinodes correspond to constructive interference. The nodes, which are these parts right here, you guys saw in the demonstration, these parts that weren't moving at all, the nodes, were the result of destructive interference. Remember, this only occurs at very specific frequencies. If you go a little bit above or a little bit below, you don't see this pattern. It doesn't look like it's standing still. The interference pattern isn't random, but it appears to be random if I increase or decrease the frequency somewhere outside of this resonant frequency. We're going to draw now the standing waves produced by a string in a number of different scenarios now. Let's say it's a guitar string. It doesn't have to be a guitar string. It could be any string, the demonstration that we just did, or it could be a guitar string or some other musical stringed instrument, or it could be anything, like the chain of a swing set. If you start vibrating that at a certain frequency, anything that is like a string. If it's attached at both ends, and I pluck that string, the first standing wave that I will see will look like this, where you have two nodes and one antinode in the middle. Now, the second one that you see, when I crank the frequency up, will look like this. Where you have three nodes and two antinodes. Crank the frequency up even more, like we did in our demonstration, then you're going to see something that looks like this. Where you have four nodes and three antinodes. And we could keep going. I'm not going to draw the next diagram, but you can imagine if I did, we would have 5 nodes and 4 antinodes, then 6 nodes and 5 antinodes, and so on and so on and so on. So you pluck your guitar string, you can generate all kinds of frequencies in that string, like thousands of different frequencies. But most of them don't stick around. Most of them die out very, very quickly because they don't correspond to a resonant frequency. The ones that stick around in that string are the standing waves, the ones that correspond to a resonant frequency. Let's say we're designing a musical instrument. We want to determine what the resonant frequency of this is so that we can generate music as opposed to just noise. Let's derive an equation that describes at what frequency this will occur. Let's first define the length of the string as L. Length of the string is L. Now let's define the length of the string in all three cases in terms of the wavelength. So I'm going to draw over here off to the side a wave. Okay, now this is a complete wave, right? It's more than one complete wave, actually. If I'm going to look at this first one up here, and I'm going to trace it out on this wave, how much of a wave do I have here? How much of a wave is that? Is that a full wave? Is that a half a wave? Is that a quarter of a wave? What is that? How much of a wave is this that I just traced over? Same wave that I have in the first diagram there, yeah? That's a half a wave. So I'm going to say the length of this is 1/2 of a wavelength. Does that make sense? Let's look at the next one. The second one there, you can see the wave goes from here, starts here, goes all the way to here. How much of a wave is that? Jacob? Yeah, that's a full wave. So we're going to say that L, the length of the wave, is equal to 1 complete wavelength, lambda. Let's look at the next one. We start here, we go over here, and then we go through that and back to here. How much of a wave is that? Is that 1 wave? Is that a half a wave? What is that? 1.5? It's 1.5? Now, you could say 1.5, but I'm going to do it in a fraction. You'll see why I'm going to do it in a fraction in a little bit. The fraction for 1.5 is 3/2. Doesn't really matter, but it's easier to see a pattern later on if we make it that improper fraction 3/2. So I'm going to erase this now because we've established all the lengths in terms of the wavelengths. Now what I want to do is rearrange each of these to solve for lambda. Lambda is equal to 2L, right? 2 goes up by multiplying, 2L. Well, this one's easy. Lambda is just equal to L. This one, lambda is equal to 2 goes up, 3 goes down. Lambda would be equal to 2/3 L. Now remember, the wave equation, the universal wave equation that we learned a little while ago. V is equal to F times lambda. Rearrange it. We get F is equal to V over lambda. F is equal to V over lambda. F is equal to V over, what's lambda? 2L. So the frequency at which the first standing wave would be produced in this string would be V over 2L, the speed of the wave divided by 2 times the length of the wave. In our demonstration, we talked about how to change the pitch of a guitar string. One person said tune it, which means tighten it or loosen it, right? If you tighten it or loosen it, you change the speed of the wave. When you change the speed of the wave, you change the resonant frequency. So therefore, you're going to hear a different sound. What was the other way to change the pitch of a guitar string, Dylan? Put your finger on a fret, which changes the length of the string. By changing the length of the string, it changes the resonant frequency. You hear a different sound. Okay, when you put your finger on a fret, do you hear a higher sound or a lower sound, Dylan? Higher pitch, right? Higher pitch. Why? Well, because when you put your finger on a fret, you're effectively reducing the length of the string. And as L gets smaller, F gets bigger. The resonant frequency that you hear gets bigger. Okay. We're going to say F is equal to V over lambda for this one as well. We're going to sub in, well, we're just going to sub in L for lambda here. And the equation becomes F is equal to V over L. So the first standing wave that would be set up would be V over 2L. The second one would be V over L. Let's see what the third one would be. F is equal to V over lambda, which, if we sub in 2/3 L, right, for lambda. Then we get v over 2/3 L. I don't like that, though. That's kind of a little bit messy. So let's just simplify that a little bit. We end up getting v over 2/3 L. Divide by 2/3 is the same as multiplying by 3/2. So F is equal to 3 over 2 times v over L. That would be the third standing wave that would be set up in that string. Okay, when I did the demonstration a few minutes ago, if we had have known the speed of the wave in that string, we could easily have measured the length of the string. And we could have absolutely calculated the first frequency, and it would have matched up with the frequency that we determined it to be, which was 5 hertz. And then if we had used the second equation, we could have calculated the second frequency to be 10 hertz. And then we could have calculated the third frequency to be 15 hertz, and so on. This one right here, we're going to put a little subscript 1. The reason we're going to do that is because it is the fundamental, running out of space there, but try to write that in. It's the fundamental frequency. Or sometimes we call it the first harmonic. This next one we're going to call F2. And the reason we're going to call it F2 is because it's twice the value of the first one, right? A half V over L and V over L. So it's twice the value of the first one. We'll call that the second harmonic. 2 times the value of the first harmonic, or 2 times the value of the fundamental. This one, like what's F1? V over 2L, sorry, V over 2L, yeah? This one is 3V over 2L. This is 3 times the value of the first one. So we're going to say F3 is 3 times F1, and we're going to call that, what do you think we're going to call that? It's the third harmonic. So you can see that the first harmonic is whatever the value works out to be. The second harmonic is twice the value. The third harmonic is 3 times the value. Now there's a lot of stuff up here. The good news is when you actually solve problems, it's easier than what you see up on the board. The reason is because you only ever really and truly have to deal with this one, the first harmonic. Because if you've got a second harmonic problem, well, just treat it as a first harmonic problem and then double it. If you've got a 14th harmonic, then treat it as a first harmonic and then multiply it by 14. So we have to be able to derive that equation for F1, but for F3, we just need to remember it's 3 times the value of whatever F1 was. Okay? I'm going to do a question. This is the question that's on the handout that I've given you here now. First question says a 25 centimeter long string is set in vibration. The speed of the wave through the string is 500 meters per second. What are the first 3 possibilities for harmonics? Or what are the first 3 resonant frequencies in the string? Remember what I said a minute ago? You can derive an equation for the first harmonic and the second harmonic and the third harmonic. Or you can just deal with the first and then multiply it by 2 and 3. So that's what I want to do. I'm going to draw the picture here. This is the first harmonic. We know that L is equal to 1/2 of the wavelength, and lambda is therefore equal to 2L. The frequency is V over lambda, but we're going to replace lambda with 2L. So my equation becomes, for the first harmonic, F is equal to V over 2L. Let's calculate that first harmonic. V is 500 meters per second. 2 times L, we got to make sure that's in meters, 0.25 meters. So we get 500 divided by 0.50, which ends up giving me 1,000. 1.0 times 10 to the 3 hertz. The first harmonic, or the first standing wave, would be 1,000 hertz. Now, you could derive the equation for the second and the third, or why don't we just say F2 is equal to 2 times F1. There's the second, and the third is 3 times F1. Does that make sense? Do you see how we really just have to be able to do the first one, and then the second one and the third one just kind of fall into place from that? On your worksheet, please do questions 1 to 4 for tomorrow, please.